So finally, let's look at some fun examples of recurrent neural network outputs, or what we can do with them. So this is just text prediction. So here we really do letter by letter text prediction. So we code every single letter by a class and we train on a large source of text to predict the corresponding next letter. And now you see this is actually text that looks valid. It doesn't make too much sense, one has to say. The surprised investors weren't going to raise money. I'm not the company with the time. They are all interesting quickly. Don't have to get off the same programmers. There is a super angel around fundraising. So you can see it picks up a lot of things that seem to make a little bit of sense. The whole thing doesn't make a lot of sense, but words that have related meanings and often appear together, but also you basically generate completely valid words. Yeah, so this is letter by letter prediction, but the words are valid. And there are sentences, there are full stops, there are apostrophes, there's a citation here, there are commas. So this picks up a lot of meaningful things. Next, let's look at training a larger source of text on poetry. And this is basically an RNN which generates Shakespeare text. So it reads Shakespeare text as inputs and it makes up new Shakespeare text. So RNNs are generative neural network for sequential data. And you see here, this is really impressive. So you see a formatting in the way as you see Shakespeare poetry being formatted with these citations here from different people, Viola and King Lear in this case. And it's very poetic. Why Salisbury must find his flesh and thought, that which I am not abs, not a man, and in fire. So it really reads like poetry. I'm not sure if it makes a lot of sense, but perhaps it makes a similar amount of sense as much poetry does. So, and finally, this is really a fun example for scientists. So we can do this. We can take LaTeX source code and train again letter by letter to generate LaTeX source code. And this is using just math papers as a source. And the output, well, is not always correct. There are some syntactic errors that have to be manually corrected. But it almost compiles. So with minor corrections, this works, and it generates things like this. So there are theorems, there are proofs, there are comments and equations. Some of the references don't work apparently, but clearly the RNN thinks it has proven something, and it goes on like this. So this is really fun. Of course, this is still quite a bit away from generating meaningful text from a human perspective. So deep text that has a deep meaning and makes a lot of sense if you really look over long distances of the text. But you can do extremely impressive things with modern state-of-the-art RNNs and transformer networks, which are essentially also recurrent structures. So this is going quite a long way at the moment. Okay, so with this, we are finished for the RNN, Recurrent Neural Network lecture. So in this lecture, we have seen that recurrent neural networks can be used to encode time sequences because we have a definition of a neural network function which updates a current cell state based on the previous time step, and we can use that because we use parameter sharing, we can use that to predict arbitrarily many time steps, as many as we need to encode a sequence of desired length. We have seen that there are so-called universal RNNs that can learn arbitrary algorithms. We have seen that there is a trick called unfolding, of RNNs in time, where we write the individual time step evaluations explicitly, and then we turn the recurrent neural network into a feed-forward neural network that goes from input to output sequences, and we can train those networks with usual backpropagation at the expense of spending more computational effort because we have to train on many time steps simultaneously. So we have a larger network, basically. We have seen that there is a trick called teacher forcing, where we can separate these individual time steps during training time at the expense of giving some expressivity of the neural network. And we have learned that there is an important RNN structure that is called LSTMs, which solves the problem that networks that are deep in time are deep, so they go through many nonlinearities and are otherwise hard to train. And then finally, we have seen several examples of RNNs or RNN outputs and predictions. So RNNs, recurrent neural networks, are a big topic in machine learning, and one could give a complete lecture just about that. I'm not going to do that here, but rather stop at this overview of RNNs and go on to the next topic. But I very much encourage you to look more into RNNs, especially when you're dealing with sequential data processing, such as translation of text, for example, or any kind of processing that is based on text, on audio streams, also on video streams, etc. And with that, thank you for your attention and see you in the next lecture.